In this video, I'd like to discuss the basics of graphing exponential functions. So you can see I have this example, y is equal to 2 to the x power. And generally with exponential functions, you'll see the variable as the exponent. And one way to graph pretty much any function is you can always start with a table. So we can plot different values of x and see what the y values would be. And then once we have a collection of essentially coordinate points, we can plot them and then connect them with the curve. So let's start with the value of 0, and 2 to the 0, or really anything to the 0 power, is always going to be equal to 1. Next, we can plug in x equals 1, and 2 to the 1, or 2 to the first power, is just 2. When x is 2, we have 2 squared, which is 4. When x is 3, we have 2 cubed, which is 8. So you can see this grows pretty quickly. The next, when x is 4, y is 16. When x is 5, y is 32. And essentially every x value, every time you increase by 1 for the x value, your y value multiplies by 2. And that right there is kind of the key feature of exponential functions. And that basically every time you increase by 1 in the x direction, you multiply by some number. Okay, and it doesn't have to be a number greater than 1, it could also be a fraction. And that's what's known as exponential decay, where this is exponential growth. And notice we can also evaluate this for negative numbers. So if I put in negative 1, 2 to the minus 1 is just 1 over 2 to the first, or 1/2. If I put in minus 2, I get 2 to the minus 2, which is 1 over 2 squared, or 1/4. And let me extend this. If I put in minus 3, then I have 2 to the minus 3, which is 1 over 2 cubed, or 1/8. And you can see as x gets more and more negative, this y value essentially starts to approach 0. But one of the key points is to recognize that no x value can ever make y equal to 0. No matter how big of a negative number I put in here, it's always going to be slightly bigger than 0. So now that we've completed our table, let's actually get a picture of what this graph looks like. And now that we have a coordinate plane, we can actually plot these points. So we have 0, 1, 1, 2, 2, 4, 3, all the way up to 8. 1 is 1/2, negative 1 is 1/2, negative 2 is 1/4. And basically what you'll see is that the graph will hug essentially that x-axis and then slowly start to rise, but then eventually kind of shoot off to a much higher value. So these exponential functions might start growing very slowly, but eventually once they pick up some speed, essentially, they go to a very high value very quickly. And one key feature of this graph is this x-axis. It's acting as what we call an asymptote. And an asymptote is essentially a line that the function will not cross. So that line is y equals 0 in this case. The function will just never cross that, since there's no x value that can make y equal to 0. So this function here exhibits what we call exponential growth. But we could also look at a very similar function if we had 1/2 to the x power. So now our base is less than 1, though it always has to be bigger than 0, or else you deal with imaginary numbers. But if it's between 0 and 1, this is what we call exponential decay. So this is the case of growth over here, and this is the case of decay. And basically, it'll still go through the point 0, 1, but then all of the values are essentially flipped or reflected about the y-axis. So minus 1, 2, minus 2, 4, and so on. So this function comes down like this, and the asymptote's still the same. It's this x-axis, or y equals 0.